morning, good afternoon, wherever you may be in your day. Thank you as always for choosing that chemistry part of your day. I want to talk a little bit about the molecular models and making the right model. So let me start with some basics. Each ball represents an atom, really a nucleus and a point of the geometry. Black is typically carbon. It's always going to be 4 holes in tetrahedral in geometry. White is always hydrogen and always just one attachment. And then the rest is typical in a set. Typically the set's red or oxygen and it has 2 holes because it can form up to 2 bonds. And then the various other, and then green tends to be halogens, silver tends to be a generic metal. And then you have 2 types of sticks, or connectors, if you will, in the sets. A short, thick one, and a thinner, longer, bendier one. The thin ones, the small ones, the small, thick ones that don't bend, they are for single bonds. The ones that are longer and bendier, those are for double bonds. So if I want to make a single bond from carbon to oxygen, I just put in one of the stiff connectors and put a black and a white on there, and voila, we have a carbon attached to a hydrogen. If I wanted to then double bond to an oxygen, I would get 2 of these longer ones, like such, and then I would put one in the red and then bend it around like that to do a double bond. So this would be C double bond O with 2 hydrogens on it. Now what's neat is the single bonds can spin, and this is true in the molecule as well. The double bonds can't spin, and that's true of the molecule as well. So in some of these chemicals that you build, I need to build something slightly larger here for you to demonstrate this. If I can find the right pieces, that is. And when we're talking about some of these chemicals, let's take this for example. Something like this. All these bonds can spin and turn, and now you can really see where they're turning. So this chemical might at first glance look different than this, but it's the exact same chemical. I didn't have to break any bonds to go from here to here, and that's true in the molecule. It's spinning, it's all the same molecule. It can turn like this in real time. The double bond locks that piece in place. So again, build 2 structures and compare them. If you can turn them, twist them, and make them look exactly the same, it's the same chemical. It's not a new chemical. But if you have to break a bond and move where something's attached to make that new model, you've created 2 different chemicals. They can look really similar. Your left hand and your right hand look really similar. But if we were to cut off your hands, don't do this, and then sew them back on to the other side, you'd notice that your left hand was on your right arm and your right hand was on your left arm. They are not the same. They are similar, but they're different. And chemicals are the same way. We can have a right-handed version, a left-handed version, or a mirror image of each other, and they can have really different chemical effects. So subtle differences, but important. So in a lot of these cases, if you're trying to decide, is it different? Either make 2 models, or you make a model, and then the group next to you, have them make a model, and then compare the 2. And that's the best way to go through this lab. And that's really it. If you want to see how those lone pairs affect geometry, you can put one in. They take up space. They push down on the other bonds, but they're not actually part of the structure itself. So again, if you want to keep it out like that, that's where the angles are. If you want to see that lone pair and why they're pushed down, this helps explain it. You may or may not want to use the paddles or the lone pairs, but that's what they're there for in the kits. And that's all there is in the kits. Have fun working through the lab. And as the acorn said when he grew up, geometry.